I made myself a couple of notes here of things to mention when I came back to this. Hey, why'd you do these things, Steve? One of those is, why did I draw this spring also in tension? Cable has to be in tension. But why did I draw the spring pulling up? Well, if you look at what's going on here, we've hung a weight from a cable on this side and a spring on that side. And the only way that's going to happen is if both of these are pulling up to keep that thing counterbalanced from this force going down. Now, if we had something, was pushing back with a certain amount of force, then maybe this spring was getting compressed and it's going to apply a compression force back. But the simplest answer is, I just kind of knew from experience, the only way this works is if that spring is in tension. Had we applied this in the negative directions, if I'd applied both of them in the negative directions in compression, solved and got a negative Fs, like if I'd found Fs was equal to minus 70.7, that would have told me that my initial guess was just simply incorrect. I guessed it was in tension. I got a positive value for Fs. That tells me I guessed it was correct. But again, we know that the cable can only hold tension. It has to pull. But the spring could push or pull. We guessed it was pulling this time. Also, notice I've done very little algebra here. I mean, I've done some. Do as much algebra as you need to. There is no shame with showing me more algebra. As much of how do I get from these two equations down to these answers. Do as much algebra as you need to get there. There is no shame in doing too much algebra. I promise you. It is so much easier for me to grade if you make a mistake. If you've shown all your algebra, I can find it. Okay, so do as much algebra as you need to, and then feel free to do a little more. No problem at all. Okay, I don't want to spend too much time on that. I want to keep moving and be efficient with our time, but I definitely want to make sure that we give all the detail that we need to. And again, this is lecture 4. This is the 6th page so far. Now what else? I came up with some pro tips, if you will. If you're watching this video like a long time from now and we don't use the phrase pro tips anymore, just hints, if you will. Anyway, I'm sure there will be other things in here that would date this video. But for now, we'll call it pro tips. Pro tip number 1 I came up with is, with multiple knots or rings with cables, draw free body diagram of each ring as needed. And if you want to dig in a little bit further, we're going to see a problem where we're going to have to do multiple free body diagrams here coming up next, and we'll do that throughout the semester in different situations. Now, if I add kind of another additional further pro tip on that, on top of that even, might start with the knot or ring where a known force acts. And we'll see an example of that. And I know it's just words right now, but we'll put it in the context as we go. So I'm basically writing these out and we'll refer back to them. Pro tip number 2 here. For problems involving max tension allowed in multiple cables, and it could be cables, ropes, or chains. Those are all essentially behave the same. so if I've got a problem where it says the maximum tension allowed in all the cables is 80 pounds or 100 pounds, whatever it is, figure out what's the largest weight it can support. You'll see several problems like that, right? What you want to do is you want to just be prepared to solve the problem multiple times by setting one cable equal to the maximum tension and comparing tension in the other cables. So basically you if it's saying, hey, how much can it support if this is the maximum amount? Well, you find the tension, you set one cable equal to the maximum amount, find the tension in all the cables, and if you found, well, here's a cable that has a tension that's higher than the maximum allowed, then then you're gonna have to redo the problem. And then what you can do is, well, whatever cable you found now that's exceeded its maximum allowable tension, go back and set the problem where that cable has the maximum tension, and make sure all the other cables are under their maximum tension. Or sometimes you can identify the critical cable mathematically. Alright, so again, those are some words, some pro tips, if you will. We're going to put those kind of in context. Okay. Alright, I've got a couple of problems I want to work with you here, and then we'll call it Lecture 4. And so Lecture 4, this is page 7 of something. We're going to work problem from the Hibbler text, 14th edition. We're going to work problem 311. I'll be honest with you, I had to go look up a trigonometric identity for this guy. Right? So 310 and 311 both use this diagram, but I just wanted to show it to you so you can see it, and I'm going to draw it out with you so you've got it in your notes. But that's what we're looking at. Okay? So 311, 14th edition of the Hibbler text. You've got supported up on a ceiling here, some sort of a hanger and a cable coming out of it, a vertical 20-degree angle, and that cable then attaches to the center of a pulley, and then another cable runs across that pulley this side, the left side coming across the pulley. You have a weight, W, just hanging vertically. And on the other side of this, we have somebody is applying some force F out here. And then we label these points here, and by the way, there is an angle theta between this vertical and this coming off at some angle over here. If we label these points, they label the pulley A, they label the hanging point up here B, and then they label the weight is hanging at point C, and this force is applied at point D. And so the problem is going to ask us to find the max weight if the cable from A to B and the cable from CA to D, so we've got a cable coming across here and a cable from here to here, and those two cables can only support 80 pounds. And then also, this is the challenging bit, this is what I had to go look up something for, find theta. Also find theta. What is the angle between this vertical part of the cable and this part over here? Alright, now if we go back and look at, set something back over here. Ropes and cables are often considered weightless. That means the tension is the same at all points within that cable, and also pulleys are frictionless unless otherwise specified. So since there's no friction in or on this pulley, and it's the same cable going from C all the way to D, it is the same tension at all points in this cable from all the way around. That may not be intuitive. That might take a little bit to wrap your head around, but that is the way this is going to work, is because it's the same cable going all the way across. It's the same tension all the way across. And this is a different cable from here to here, so it has its own tension, but it's the same tension from here to here all the way. So, what am I looking for? I'm trying to find the weight W. Okay. And I'm also trying to find theta. Let's start with W. So how do I do that? Well, if I draw a free body diagram, very simple, of W. What do I got? I got this box. Weight. And I've got a tension coming out, we'll call it CAD. They're both in the Y direction. Sum of forces in the X direction is equal to 0. Yes. There's no X direction forces, so there's nothing else to write there. So that doesn't do us any good. But I can write sum of forces in the Y direction is equal to 0, and I can say, well, I've got TCAD going up and minus W going down. Those add up to be 0. So one equation, two unknowns. But this is what I do know. I can't solve for a value for either of these, but this is what I can do. I can say that the tension in that cable from CAD is just always going to be equal to whatever the weight is applied there. Okay. Well, that means I need to find this tension in CAD to find what the weight is, because that's what I'm looking for. What is the maximum weight? So I'm trying to find the weight. That means I need to find the tension in this cable. Where is this cable also acting? So it's acting on the weight, but it's also acting on this pulley here. So if I draw a free body diagram then of pulley A, remember this is 20 degrees from vertical here. So that means this is 20 degrees from vertical there. Alternate interior angles are congruent. I think that's how they said it in geometry. It's been a long time since I had that geometry, but I think that's how that works. So look at your diagram here. Again, I like to draw my forces resolved on a free body diagram. So I'm going to draw my tension, that is, we're going to call this BA. Tension BA, it has a vertical component that is going to be the cosine of 20 degrees. Steve, why the cosine? Because it's this component going up here, and it is adjacent to this 20 degree angle. And I'm going to draw a tension here. That's the X component of this tension BA, and this one is going to be the sine of 20 degrees because it's going to be opposite that 20 degree angle. It's also, if this is the cosine, that means this has to be the sine. What else? Well, I've got a force over here, the tension CAD, which is also equal to the weight, but right now it's just tension CAD. And then attached here, I've also got tension CAD coming off right here at angle theta. So, over here, in the horizontal coming off in the positive X direction, I've got TCAD, and this is going to be sine theta. Yes, I know it's an X component, but it's also, that is the force that is opposite of this theta. So it's going to be sine theta, as I said. Don't tie sine to X and cosine to Y. I'm sorry, don't tie sine to Y and cosine to X. It depends on where your angle's measured from. Remember, opposite and adjacent. Force going down. So if this is the sine, and by the way, this, notice that it's pulling down to the right. So it's pulling in the positive X direction and pulling down in the negative Y direction. So this is TCAD, and this one's going to be cosine of that unknown theta. Okay. I'm right at 15 minutes. That's not a bad place to stop. We'll pick up this one and apply equilibrium.